Hello, this is Professor Roman. Let's continue the lecture series Transition to Advanced Mathematics. I'm going to wrap up our discussion of combinatorics today with something I promised to do at the beginning of this discussion, and that is show you a problem that is relatively simple sounding and yet has eluded some of the best mathematical minds for roughly the last 125 years. One of the most interesting sub-branches of combinatorics is the study of special families of subsets of a set. Some questions related to this are relatively easy to answer, whereas others are still as yet unsolved. So let me first give you two examples of relatively easy problems to solve. If X is a set of size n, how large can a pairwise disjoint family of subsets of X be? Well, to answer this question, we can observe that if we have a family of pairwise disjoint subsets of X, and if any of these subsets should contain more than one element, say, for example, A sub k should contain the elements little a1 through little aj, where j is bigger than 1, then we can split this set into singleton sets. And that can be used to enlarge the family, drop A sub k, but then include these singleton subsets. We get a larger family that is still pairwise disjoint. So it follows that a pairwise disjoint family of maximum size must consist only of singleton subsets. And so the maximum size, therefore, is the size of the set X, which we're calling n. Here's another example of a relatively simple problem. A chain of subsets of a finite set, say of size n, is a collection of subsets that has this relationship. So S1 is contained in S2, which is contained in S3, and so on. A chain is called a proper chain if these set inclusions are strict, so no two sets are equal. And the length of a chain is the number of subsets in the chain. So the question is, what is the maximum length of a chain in X? Well, each subset in a proper chain must be strictly larger than its immediate predecessor. So to get the longest possible chain, we should start with the empty set and just toss in a single new element as we proceed. This chain has n plus 1 subsets, so it has length n plus 1. And that's the longest possible proper chain. This argument could use a little bit more explanation, possibly. And I'm going to leave that for you to think about. Do you think maybe this is not entirely convincing and could use another line or two of explanation? I'll leave that up to you. Now let's turn to the problem that is motivating this section, this discussion. First, we need a definition. A family S of subsets of a finite set X is called a Sperner family over X if no member of the family contains any other member of the family. Members of the family can overlap, or they can be disjoint, but no member can be strictly contained in another member. That's not an unusual property, something you might be interested in exploring. Another term that's more common, really, than Sperner family for this is antichain. Let me give you an example or two. So let's let X be the set 1 through 6. This family of subsets is a Sperner family or antichain. No member of this family is contained in another member. But here we do not have a Sperner family because this subset is contained in this one. Here's an important example of a Sperner family. If k is an integer that lies between 0 and n, then the set of all subsets of x that have size k is a Sperner family of size n choose k. I forgot to say the size of x is n. I better add that. Okay. Now this follows from the simple fact that if you have two sets of the same size, two distinct sets of the same size, neither one can be contained in the other. So if the entire family consists of sets of size k, it's got to be a Sperner family. A natural question about Sperner families is how many different Sperner families can be formed from a set of size n. For n greater than or equal to 0, the number d sub n of Sperner families over a set of size n is called a Dedekind number, and it's named after the mathematician Richard Dedekind that we've encountered before. He defined the Sperner families and these numbers in 1897. Here are the first few Dedekind numbers. D0 is 2, D1 is 3, D2 is 6. They begin to jump quite a bit in size. Look at this last one. This number, D8, wasn't determined until 1991, almost 100 years after Dedekind introduced these numbers. Let's take a peek at a couple of these numbers, the smaller ones, anyway. Suppose n is 1. The nature of the set x doesn't make any difference, so we'll just say capital X is the set containing little x. The subsets of x are the empty subset and the entire set. And so the families of subsets, all possible families, the empty family, the family containing just the empty set, the family containing just the whole set, and the family containing both the empty set and the whole set. That's the power set of capital X. Those are the possible families. But family number 4 is not a Sperner family. The other three are Sperner families, and that's quite obvious because, for example, the one-element families have to be Sperner families because no element's contained in another, obviously, since there's only one element or one subset. When n is 2, we can take x to be the set containing little x and little y. These are the subsets of x, and this is a list of the families of subsets. We've got the empty family, the singleton families, the doubleton families, the tripleton families, and the whole power set. And, excuse me, I'm going to leave it to you to show that exactly 6 of these are Sperner families. Well, it turns out that we have this collection of Dedekind numbers. Those are the only Dedekind numbers that are known. So we're not having much luck in the last 125 years or so of determining Dedekind numbers. In fact, I'm just going to jump ahead and then I'll come back. There's a brilliant mathematician, there was a brilliant mathematician named Garrett Berkoff. I met him once, actually, at a party at Harvard when I was teaching at MIT. We had a mutual friend, and he introduced me to Garrett. Unfortunately, I didn't have much time to talk to him, but I would have liked to because he was quite brilliant. He conjectured at one point that the Dedekind numbers d sub n were always divisible by 2n minus 1 times 2n minus 2. But d5 is not. I guess d5 hadn't been discovered at the time he made this conjecture. So the interesting thing about this is even the most brilliant of mathematicians can sometimes have faulty intuition. So back to work here. We have, in a sense, verified that d1 is 3 and d2 is 6, and that's the best we're going to do. Okay, now, got the pages out of order here. Okay, here we go. Well, so it does seem that we're not having much luck finding the Dedekind numbers. Even Garrett Berkoff didn't have much luck. So let's turn to a different question, one that has been answered, and we're going to answer it. Namely, what is the maximum size that a Sperner family on a set X of size n can have? How big can a Sperner family be? That turns out to be a much easier question than how many Sperner families are there. But this is still not a trivial question by any means. First we need a lemma. And the lemma is called the Lubel-Yamamoto-Meshkelin Inequality, or Lemma, and that's often abbreviated LYM. So here's how it goes. Let S be a Sperner family over a set X of size n, and let little s sub k be the number of subsets in the Sperner family that have size k. So we're grouping the subsets in S by their size and count the number of such subsets. for each size. Then we have this inequality, and this is the LYM inequality. As to the proof, it's very clever. And so here's how it goes. Just for convenience, let's refer to a subset A of a Sperner family as a Sperner subset. So let A be a Sperner subset of size K. And consider the set of all permutations of X. I'm going to denote that by P sub A. Permutations of X of this form, where A1 through AK is a permutation of the set A, the Sperner set, followed by a permutation of the remaining elements of X. So this altogether is a permutation of X, but the first portion of it is an ordered arrangement of the elements of the Sperner set. Then comes an ordered arrangement of the rest of the elements. Okay. The fundamental counting principle tells us how many of these permutations there are. There are k factorial permutations of the elements of A, because A has size k, and then there are n minus k factorial permutations of the remaining elements. So the size of P sub A is k factorial times n minus k factorial. Now, of course, if B is another Sperner subset in S, different from A, and let's say it has size j, then P sub B has size j factorial times n minus j factorial. But the key point here is that the permutation sets PA and PB must be disjoint. Because if that wasn't the case, then there would be permutations, a permutation in PA, it's the same as what I wrote up here, and a permutation in P sub B, so it starts with a permutation of the j elements of B, and then the rest, permutation of the rest. These would have to be equal. They would belong to both of these two sets. But this is not possible, and the reason is that one of these two, either this or this, is a subset of the other. If K here is less than or equal to J, then A1 through AK is the beginning of this. So in particular, the elements A sub I are also B's, so they belong to capital B. So A is contained in B, and that violates the condition of a Sperner family. If K is bigger than J, we got the opposite problem. Then the B's are all equal to the sum of the A's. And so once again, actually this is a strict inclusion, but it doesn't matter. Then B is contained in A. That also violates the Sperner condition. So these permutation sets, P sub A, are pairwise disjoint. Okay. And that means that the sum of the sizes of all of these permutation sets, P sub A, as A ranges over the entire Sperner family, will be at most n factorial, because that's the number of permutations of X. This is the best we can say, at most, because there are quite likely to be permutations of X that don't start with a permutation of one of the sets in the Sperner family. So they wouldn't be in any of the p sub a's. So this could be strictly smaller than n factorial. And you can probably make up an example very easily. So when we sum the sizes of all the sets p sub a, we can group those by the size of A. If A has size k, then each of the S sub k Sperner sets of size k contributes k factorial times n minus k factorial to the total. So we sum this, k goes from 0 to n, and that's less than or equal to n factorial. All we have to do now is divide both sides by n factorial, and we will get the LYM inequality. So, as I said before, this is quite a clever proof. It's not terribly deep in the sense that it's difficult to understand. After you've read it a couple times, it should, become clearer. The most interesting thing about this is who thought of it first. It's quite nice. It's an elegant proof. Okay? And it doesn't involve any really deep mathematics, because we were able to go through it here in this course. Now we can use the LYM inequality to determine the size of the largest Sperner family. And this is called Sperner's theorem. If the size of X is n, and if S is a Sperner family over X, then the size of S has to be less than or equal to n choose greatest integer in n over 2. Moreover, this upper bound is realized by the family of all subsets of X of size greatest integer in n over 2. Remember, we've seen this binomial coefficient before. It's the largest binomial coefficient for a given upper number n here. As far as the proof of this is concerned, it follows very easily from the LYM inequality. So again, we'll let S sub k denote the number of subsets of size k that belong to the Sperner family. And since we do have this relationship, I just spoke about that, this is the maximum binomial coefficient for upper number n. When you put those two in the denominator under sk, you have to reverse the sense of the inequality. So this binomial coefficient goes over on this side, and this one goes on that side. So we have this inequality, and now we just sum. We sum on k goes from 0 to n. And this sum here is the sum in the LYM inequality, and so it's less than or equal to 1. But the virtue of this is that this denominator does not depend on k, so it can be taken outside the summation by the distributive law and moved to the other side. And we end up with the sum of the little sk's, which is the size of the Sperner family, is less than or equal to this binomial coefficient. One last remark about the Dedekind numbers. Actually, there is a formula, a very simple formula, discovered in 1988. And here it is. this formula, I won't even attempt to read it. It's so complicated. In fact, it's even worse because these b numbers, b sub I super k, bik, this k is not an exponent. Bik is the ith bit in the binary expansion of the number k. So you take k, you write it as a string of zeros and ones in binary, and you take the ith bit. So this formula is both fascinating and really scary. I don't know how you would ever use this formula. It's totally useless when it comes to computing the values of d sub n. Even when n is 9, there are so many terms. Look at the upper limit here. This sum goes from k equals 1 to k equals 2 to the power 2 to the n. So when n is 9, 2 to the power 2 to the 9 is 2 to the 512, which is about 10 to the 154th power. This again is way over the number of estimated number of atoms in the universe. It's a gigantic number. And that's just the number of terms in this sum. So it is impossible to write that out. And so I don't know if this formula has any value whatsoever, except for its curiosity. Okay, so that completes our discussion of Sperner families. The reason I included this was not so much for its mathematical value, but just to show you that simple sounding math problems can be quite involved. You would certainly want to think that this concept of a Sperner family, just a bunch of subsets of a set X where no subsets contained in another subset, is not that complicated an idea. Why it's so hard to find out how many such families there are is a mystery. Evidently, nobody has thought of a really good idea for dealing with this problem.